Okay, so exam I think went well. Seems to have, based on preliminary grades. We're about halfway done grading. This will be our final lecture. And I wanted to wrap up with some cautionary notes about predictive modeling. We've been spending a good bit of time in recent weeks on predictive modeling, so statistical learning or supervised learning. And while there's lots of nice techniques and methods for doing that, that whole Introduction to Statistical Learning book is all it's about. There are limitations. So I work in biological applications a lot of the time, so people who have genetic or bioinformatic type data. And classification is a big deal in that context because the idea is, what if we could come up with a cheap and quick non-invasive assay, take a tissue sample, a biopsy, or a blood sample, or urine or feces even, and run it through a newfangled technology and get a multivariate data set out. Can we use that sample to predict with accuracy whether somebody has a disease? Something like colon cancer is very hard to diagnose until it's too late because it's not easy to access the colon, and you don't typically have symptoms until it's too late. So if there were a way to create a biomarker or something like that, that you take a non-invasive sample and you get a genomic data set out of it, can you make predictions about whether they have the cancer? That's kind of a holy grail that people are shooting for in medicine. And if you go search for statistics papers or bioinformatics papers, publications by researchers who say, I created a predictive model using this type of stuff, and based on my training data, I estimate I can predict colon cancer with 92% accuracy or something. There's lots of papers like that. I have a couple myself. But there's a lot fewer actual tools that are in the marketplace. And in particular, there's only a handful of diseases where there's a real simple biomarker that can be used practically. So let me just say a couple of things about ways that an apparent model that works well for prediction may not actually work well in the real world. Even if you fit it correctly, your model assumptions are right, you assessed the accuracy in a valid way using cross-validation or a train test split, it's possible that your model still won't be an accurate predictive model. So a couple of ways that can happen. One, sometimes the data that are used as training data don't really represent the population that we have in mind. If my goal is to have a cheap, non-invasive assay that I can run in the clinic to predict colon cancer, but my model was built off of, let's say, tissue samples from colons extracted from dead patients, and they've been in a freezer for months, that disconnect between real-world sample in the clinic and a petri dish full of cells that have been stored somehow could be enough to make your model not work very well. So the things that we've learned about how to build and assess a model are really valuable tools, and they are bona fide, they are useful in the real world. But they're just, I guess, be aware that there are ways for even an apparently accurate model to not be accurate in practice. One really important consideration is, are my training data representative of the population of interest? Ideally, your sample, your training data would be a simple random sample from the population of interest. A simple random sample just means, imagine one of those claws in the video game arcade where you move a claw and reach it down and grab something. Imagine just a claw that randomly goes out and picks people from the population of interest. That's the way we would like to collect our samples. But if our samples came from people who had already died from colon cancer, or our samples are really old, or they all came from one geographical region, things like that can have bad impacts on the model overall. This book by Nate Silver has been real successful, The Signal and the Noise, or Why So Many Predictions Fail But Some Don't. Kind of goes along those lines. So there's lots of predictive modeling going on, his book says. Banks and hospitals and tech companies, everybody's doing it. And yet, many times, what's claimed to be an accurate predictive model doesn't turn out to be as accurate as claimed. So best practice is to use rigorous techniques and methods, like we've learned, and be really careful about how our training data are collected. They need to be, as closely as possible, a random sample from our population of interest. This is a good book if you haven't read it or you don't have a copy. It would be using language similar to what we've seen in class. Prediction, mean squared error, cross-validation, and stuff like that. One announcement that I've been meaning to make, one of your peers in class has taken it on himself to create a student association for data science. So if you're interested in more big data and machine learning and statistical learning, those types of things, talk to Steve Brohl and be on the lookout for, it's called DATA, right? DATA is the name of the association. It's intended to be across disciplines. It's not just statistics students. It's not undergraduate or graduate. It's open. And then in terms of lecturing today, I thought I would spend some time on support vector machines, which is basically the last predictive modeling technique that's presented in the Introduction to Statistical Learning book. I've mentioned this before as a complex model. So if linear regression and linear discriminant analysis and logistic regression are relatively simple models with high interpretability, low variability, potentially high bias, support vector machines, random forests, and nonlinear models are more complex, less interpretable, less biased typically, but more variable. Support vector machines in particular are arguably the gold standard these days for just brute accuracy in prediction. They can be extremely powerful. So let's see the big picture of what they do. The idea is if we have p-dimensional feature space, so we have p predictor variables. Suppose we have 2 predictor variables. Can we find a one-dimensional boundary that can separate the classes? Support vector machines takes a p-dimensional predictor variable space and tries to find a lower dimensional boundary where to this side you classify one thing and to the other side you classify another. Sometimes you can do that perfectly. Given a trading data set, there is a boundary that perfectly separates your classes. More realistically, you can't. And so the task is to find a boundary that best balances getting the right predictions with the wrong ones. So the lower dimensional boundary idea in math speak is a hyperplane. So a hyperplane is basically a flat curve. In 2 dimensions, it's a line. In 3 dimensions, it's a plane, and so on. So if we have p variables, we're going to be looking for a plane in p minus 1 dimensions to use as a boundary. Hyperplane is just a linear function, so we can write it as a linear function like this. If we have p predictor variables, a formula for a hyperplane would be a linear combination like this of the p variables. When p is equal to 2, like I said, the hyperplane is a line. So with training data, what SVMs will do is try to fit models of this form to find hyperplanes, lower dimensional boundaries that separate well. I'm going to skip that. So let's look at these pictures. Both scatter plots have the same points on them, and those are our training data. Each point is an individual in our training data set. And p is equal to 2 because we have 2 predictor variables. x1 is on the horizontal axis and x2 is on the vertical. The colors might be hard to see, but bottom right is kind of a purple, top left is a blue, represent classes. We have 2 classes in this case. And our goal is to predict, are you in the red group or the blue group? In this case, the coloring represents true class membership. So in this case, if our goal is to find a hyperplane in 2 dimensions, a line that separates the blue from the red, we have many choices. All 3 of these that are drawn would satisfy our goal because they all perfectly separate blue from red. Just to be clear, if I were to pick this line, the one that looks closest to the line of equality, my prediction would be any individuals with x1, x2 values that are above that line, I'm going to predict blue. And any with x1, x2 values below that line, I'll predict purple. Okay. So in cases where we have many choices, why should I pick any one of these over any of the others if they all separate perfectly? We can still impose some kind of optimization criterion. For example, the line that I was highlighting a moment ago that looks like the line of equality is arguably better than the steepest line, from the perspective that the steepest line, this purple is awfully close to the boundary, and that blue is awful close to the boundary. That means there's like less margin of error with this particular choice of a line, whereas the line of equality one has greater buffering between it and the individuals. So if I had these 3 lines as a possible choice, I would pick the one that looks like the line of equality from the perspective that it seems to spread them out with as much cushioning as possible. So here is the starting point for building an algorithm. How would you go about doing this, finding a hyperplane? You can write it down as a mathematical expression. Let's see, what do they call M? I'm actually not sure what their point on this slide is. let me keep going. There is a function in R called SVM. It comes in a special package that you have to install, cryptically called E1071. But it is relatively easy to use SVM in R. You just call the function, and the syntax is similar to the other predictive models we've used. While it's easy to call the function, getting the most out of an SVM often takes some work. Tuning an SVM model is more involved than tuning a linear regression model, say. So in this picture here, we, like in the previous one, can perfectly separate the blue from the purple. There are multiple lines that would achieve that. If our goal is to find the best one, we could formulate our problem as, I want a line that perfectly separates the two classes such that these kind of boundary distances, the distances from my training individuals and my boundary, I could try to maximize that. Let's try to find a line that separates the two groups. And if there's multiple choices that would satisfy that, let's pick the one that maximizes the distances. Could be like a sum of square distances between the training points and the line. Here's another case, not the same data, where that task of finding a line to perfectly separate the classes is not possible. The points are overlapping such that there is no linear boundary that will separate them perfectly. You pick any line going through this scatter plot, you will result in at least one error. So this is an example where it's not perfectly separable. Keep going. When there is imperfect separation, we have to make trade-offs where we have to find like the best balancing line. Even if I can't get perfect separation, we find the one that gets closest. So mathematically, a support vector machine is an optimization routine. We want to maximize an objective function. So this could be minus log times the error rate, or it could be a likelihood, but some objective function that's specific to our data, subject to a regularization constraint. If I have p-dimensional data, and my goal is to find a p-1 dimensional hyperplane, if I represent my model with this expression, that has p coefficients in it, or p plus 1. So in order to knock the dimension down by 1 unit and be working with hyperplanes instead of p-dimensional surfaces, we impose a restriction. So if you enforce that the sum of the betas equal a constant, that's where the requirement of a hyperplane is enforced. So that's pretty abstract, and I don't know that they have any more detailed examples of, for example, picking M. But at least big idea is optimization routine, looking for hyperplanes, a line or a higher dimensional line, hyperplane, that gets closest to separating and maximizes the little margins from the boundary and the actual training points. doing here? I'm not sure what they're doing with that slide. Definitely, if our goal with SVMs is to find linear boundaries, there can be cases where linear just does not work well. Like these data. You've got a cluster of purple points in the middle, and they're in between two clusters of blue points. So draw a line, you'll always be right in the middle of all of it. So a linear boundary will not always work. What you can do is continue with a support vector machine approach, finding a hyperplane, but you can extend the boundary to actually be nonlinear. So support vector machines aren't necessarily linear boundaries. The vanilla version of support vector machine is lines and hyperplanes. But we can get more sophisticated with the model to allow for nonlinear. So for example, when we were talking regression and nonlinear regression, we talked about representing the relationship between y and x with a polynomial. So instead of just y is beta 0 plus beta 1x, we could include beta 1x plus beta 2x squared. That allows some curviness. So we could play with expanding that linear model at the beginning of our discussion here. Like this. So if we had two predictor variables, x1 and x2, the vanilla SVM would use a boundary of the form beta 0 plus beta 1 x1 plus beta 2 x2. That would specify a hyperplane. If we want to allow for it to be a curvy surface, one strategy would be to put in quadratic terms and maybe their cross product between x1 and x2. So that's going to result in curves. The boundary of an SVM with a nonlinear model is itself nonlinear. This is an SVM that has been fit to the same data from a couple of slides ago, where a line would not work, an appropriate polynomial would work pretty well. The boundary of this SVM shows up in two places, and it's curvy. So it's more flexible and able to accommodate more complex relationships in the training data, like this one. When you fit an SVM, you go to R, you library in that E1071 package, you load your training data, and you call the SVM function. One of the considerations is what kind of flavor of SVM do you want to use? You want a linear model? Do you want polynomials, or what? That's one place where you can tune the model. Use cross-validation and try several different flavors of SVM and pick which one has the highest accuracy. Behind the scenes or under the hood, so to speak, in the program that you run, if you ask for nonlinear SVM, you won't generally end up working with polynomials. Even though polynomials are easier to visualize, I can write that beta 0 plus beta 1 and so on, that I can see the squares. They can be computationally challenging. So the authors call them wild. There's a better way to achieve basically the same thing. So the math lingo is that we use something called kernels. When you do SVM, you have to consider, do I want a linear or curvy or whatever? And the way you specify that is by a choice of kernel. The SVM function in R will have an argument for what kind of kernel do you want. Let me load the SVM package real quick. So I need library E1071. And we'll library that. And let's do question mark SVM. All right. So the basic syntax is done with a formula. So that's of the form y tilde predictor variables, like we've done with LM and logistic regression. So SVM, the class variable tilde my predictor variables. And then here are other arguments. One of them, as I was mentioning, is kernel. So kernel has to do with how are we going to parameterize the boundary function. I'm searching for boundaries. I could make it a hyperplane, a linear surface. Or, in cases where that doesn't work well, we can use nonlinear. So here is the argument where we specify what kind we want. Kernel equal linear is the vanilla version of SVM. Polynomial is what it sounds like. It's just a polynomial. But better to use one of the last two instead of polynomial, because polynomials can get computationally unstable. If you're squaring and cubing predictor variables, those numbers can get really big. And as you have really big numbers being added and subtracted and stuff, you can lose a lot in rounding. So radial and sigmoid kernels are alternative ways to code up nonlinear boundaries. We can also specify, at least in the polynomial case, we can specify the degree. So that's another parameter. If we were going to use a polynomial basis, that's another parameter that we could try to tune. If we use any other kernel except for linear, here's yet another parameter that can be tuned. Here's yet another. Here's yet another. So when I said that SVM requires more expertise to apply well, this is kind of what I had in mind. There's several things that can be tweaked with an SVM. When we did logistic regression, the natural thing to tune was the posterior or the probability of one class. You do logistic regression, you get an estimated probability, and if it's bigger than 0.5 in the Hall of Fame case, we predicted Hall of Fame. But then we considered, what if we change 0.5 to be something different? But we only had that one thing to tune. In an SVM model, we have a handful of things. So conceptually, it's not all that harder. You could just have a bunch of loops where you loop over a range of gammas, you loop over a range of degrees, loop over some different kernels, and use cross-validation throughout that whole thing. But as we know, nested loops in R, especially with big data sets, are very slow. So it can take a lot of time to build an SVM that is highly accurate with a real-world data set. This slide and the next couple are mathematics behind how to code up these nonlinear boundaries. We don't have to go through it. It has to do with cross products and inner products of the predictor functions, and then depending on what form of the specific relationship we choose, it corresponds to one or the other of these kernel functions. For your purposes, in an applied setting, you download your data, you use the SVM function, and try a few of the kernels. That's what I typically do if I use SVM. I'll try a linear kernel, I'll try a couple of the nonlinear ones, and I'll just pick the one that works best based on cross-validation. Here's an example of a radial kernel. So this is SVM, but it does not look linear at all. It's not a linear boundary. We used what's called the radial kernel. That was the third one on the list that we saw: linear, polynomial, radial, and sigmoid. So with the radial kernel and the same training data from a few slides ago, we get a very nice boundary. The polynomial boundary had two curves that did pretty well in separating blue from purple because it delineated on two sides. The radial kernel appears to do even better. It's very able to be very specific to a kind of an island of points that are off by themselves. It's not a circle, it's not an ellipse, it's not polynomial, it's not a line. It's highly flexible. Okay. I think, yeah. Have I talked about ROC curves in class? Receiver operating characteristic curves? I don't recall if I have. Let me tell you what those are real quick so I can explain this slide. Suppose that we have y as our class variable and it's binary. So like the Hall of Fame data. You're either in the Hall of Fame or you're not. If we have a classifier, so if we say that y is some function of predictor variables, then using training data, we can estimate that function and make predictions y hat by using that estimated function and plugging in a particular individual's profile of predictors. So F could be anything we've seen. Could be a regression model, could be a lasso model, could be LDA. Some way of relating y to the x's. Once you build a model and use it to make predictions, we have a breakdown, what's called a confusion matrix, where we can cross-tabulate which of our predictions were correct and which ones were incorrect. Because there is more than one way to be incorrect, we have some special lingo that we use to designate what type. In the first row, that x in the first row, that's when the truth is 1, but we predicted 0. So we falsely predicted no. Falsely predicting no is referred to as 1 minus the specificity. So let me define these quantities. I'm pretty sure we've seen these. Sensitivity And how about, let me give some names to these cells, A, B, C, and D. So if I had training data, 5,000 individuals, and I built a model, and then I used the model to make predictions, A of them will have been true zeros that I correctly predicted as 0. And B of them will have been true ones that I incorrectly predicted 0. A plus C plus D is the sample size. Yeah. So sensitivity is the proportion of true positives that we correctly classified as positive. Sensitivity is a true positive rate. So out of those who are true positives would be B plus D. That column of ones, those are all the individuals who are truly positive. Sensitivity is what proportion of them did we correctly classify as positive. Where specificity is what proportion of true negatives did we correctly classify. So both sensitivity and specificity are like positive characteristics. You want high values of both. You would like to have high sensitivity and high specificity. In the Hall of Fame case, remember that we could have really good sensitivity but horrific specificity and vice versa. If we always predict no, nobody's in the Hall of Fame, then we have perfect specificity and perfectly wrong sensitivity. So that's why we care about both of these. You don't want to maximize one without respect to the other.
Isn't the first part is the sensitivity and the like A, the block here, 0 and 0, prediction 0 and truth is 0 because of the sensitivity?
I didn't hear you very well.
The truth is 0 and the predicted value is 0. Isn't that sensitivity here?
Sensitivity is the positive, true positive rate. So it's the proportion of true positives that are correctly predicted as positive. So I think I have it written correctly.
Which is the positive, which is the negative, corresponding to 0.
So I'm referring to 1 as a positive, yeah. So like a. So this might be not Hall of Fame, and this is Hall of Fame. The proportion of true Hall of Fame players who we correctly predicted were Hall of Fame. Sensitivity is true positives. Specificity is true negatives. The reason I brought sensitivity and specificity up is because when you have this type of context and we're trying to pick a model that is best in some sense, we need to account for both of these error rates or accuracy rates simultaneously. I don't want just great sensitivity at the expense of specificity and vice versa. So what's called an ROC curve, or receiver operating characteristics curve, specificity, has 1 minus the specificity on the horizontal axis and sensitivity on the vertical axis. I don't know why it's 1 minus on the horizontal, but that's just convention. That's what is meant by an ROC curve. So this is an ROC curve. And consider, suppose we have one tuning parameter, like posterior probability of in the Hall of Fame. We're going to tune on that. Should I predict Hall of Fame if the probability estimate is bigger than 0.5, or should I predict Hall of Fame if it's bigger than 0.7 or 0.2 or what? So imagine that we did cross-validation, and for each of a bunch of choices for that threshold, we built the corresponding model and applied it and got its sensitivity and specificity. Then we could make a plot so suppose we made a picture like this. Each dot is corresponds to one of the threshold choices we're considering. Each threshold corresponds to a sensitivity and a specificity. So the threshold itself is not shown on the picture, but each dot corresponds to one threshold choice. So if you make a picture like this, and then you could connect the dots with a smooth curve, that's an ROC curve. And the goal is to pick a region that best balances specificity and sensitivity. An optimal classifier would have really high specificity, which would be really low on the horizontal axis, and really high sensitivity, which would be really high on the vertical axis. The optimal place for my curve to be then is top left. If this was one predictive model, like logistic regression, say, and I had one tuning parameter that I was considering, then my final model would be the one that corresponds to the threshold, which dot underlying that red curve gets me closest to the top left. So I might pick that model right there. Whatever threshold that was, it gets me relatively high specificity while at the same time relatively high sensitivity. I could increase the sensitivity. There are higher values of sensitivity, but they all happen at increasingly poor specificity. So as you go to the right, in particular, sensitivity continues to go up, but specificity is going down. So I'll go show you an example of an ROC curve in the slide in just a second. What they have in the slide is, suppose you had multiple models you wanted to consider. This red curve is a logistic regression model, maybe. Did you have a question?
Yeah, so you said each dot is corresponding to a threshold.
Yeah.
So does this threshold mean the kind of the marker to predict like which classes does it belong to? If it's like 0.5?
That's what I mean by threshold. Like if we were doing logistic regression, for example, we fit the logistic regression model, and then for an individual, we plug in their covariates. We get a log odds estimate. We can turn that into a probability estimate with algebra, and then that's the basis that we use for prediction. If that probability is bigger than a threshold, we'll predict Hall of Fame. If not, we won't. And it's that threshold that we're considering.
Can those classes be more than two classes?
Can the classes be more than two classes? Yes, they can. ROC curves, since they are sensitivity specificity, they're most naturally in the context of a two-class problem. But it is feasible in more than two classes to consider a threshold, and you wouldn't only be looking at sensitivity and specificity. You'd have to consider all types of errors. But you could do the same kind of search. So you'd have a bigger confusion matrix, and yeah, the same idea can be applied, but it's a little bit more complicated to do it in practice. So suppose we had training data and we fit a logistic regression model, and based on cross-validation, we tried different tuning parameters, and we have the red curve. We might consider an alternative model, a totally different model, like LDA, say. And if I want to choose between the logistic regression model or LDA, an ROC curve tells me about that as well. You can make two of these on top of each other and kind of visually compare the performance of them. So in this picture in the slides, this is an ROC curve. They labeled it a little bit differently than we did. False positive rate, same thing as 1 minus specificity. True positive rate, same thing as sensitivity. And on an example data set, one of their examples, they considered different versions, different tuned versions of both of those two models, of an SVM model and an LDA model. And the red and blue curves correspond to those two different models. The right picture is more interesting. Here is all support vector machines. This is all the same training data. And there are multiple ways to tune an SVM. So here are 4 versions of an SVM and an ROC curve for each. If I tried these 4 flavors of SVM, this gamma stuff has to do with the kernel. Which kernel should I use? You can't know that really without trying a few of them and comparing them. So here we're trying to kind of tune our SVM, and we have 4 flavors of it we're considering. If I were to pick one of them, I would pick the purple one because its ROC curve gets closer to the top left. If you have a collection of models that you're considering, an ROC curve makes it easy to visually, real quickly, choose among them. The better model will be the one that gets closer to the top left because that gives you a better trade-off of sensitivity and specificity. Here's another example, ROC curves. ROC curves are used a lot in biomarker research. So people who are looking for a simple rule to predict whether you have cancer or don't have cancer. We'll get a big training data set, and they'll try all sorts of models. They'll make a picture like this to pick the best model. You could essentially get the same conclusion without using an ROC curve if you used an overall measure of accuracy, like a single number summary of accuracy, like balanced accuracy that we've seen. If you average sensitivity and specificity, then you could just look at that one number and pick the model that gives you the biggest value of that number. But an ROC curve is a nice visual tool, and it's used a lot in practice. This speaks to your question about what if we have more than 2 classes. SVM, as defined up to this point, is all about 2 classes. We're trying to separate the purple points from the blue points. It is possible to apply SVMs to more than 2 classes. If it wasn't, they wouldn't be used nearly as much because many real-world problems have more than 2 classes. The challenge is that SVM is set up for the 2-class problem. So you have to do kind of an algorithmic hack to adapt SVMs to more than 2 classes. Here's 2 ways of doing that. The OVA, that stands for one versus all. And so in this case, you would fit, if you had K bigger than 2 classes, like let's say 3 classes, then we could fit 3 different 2-class SVM classifiers. Each one of them would be 1 class compared to all the others. So if you did that, if you changed your 3-class problem into just class 1 versus everybody else, then it's just SVM as usual. So you could go through every class and do that. Let's do class 1 and fit an SVM class 1 versus everybody else. Then let's do class 2 versus everybody else, and so on. So then, in that case, if you had, say, 3 classes, you would wind up with 3 classifiers, 3 SVMs. And the way that you would turn that into a single prediction would be plug in an individual to the class 1 versus everybody else classifier, plug it into the second one, and plug it into the third one, and get the objective function, which is a measure of goodness of fit, and classify to whichever one has the best fit. So roughly speaking, one simple way to extend SVM to more than 2 classes is to just do one versus the others and fit a separate classifier for every class, and then classify to the one that has the best fit. A more computationally intensive alternative is 1 versus 1, in which case you can consider all k choose 2 pairwise classifiers. So if k is reasonably large, that's a lot of models that have to be fit. If k is not too large, you'll almost certainly do better with the 1 versus 1 because it's more comprehensive than the other one. I'm not sure how easy it is to use the SVM function in R when there's more than 2 classes. I haven't actually done that. All the examples I've used have been 2 classes, but I'm sure it can do it. Okay, we are out of time. Let me see if there's anything in the last 2 slides worth saying. Here's some general guidance on which of some of these techniques that can be used interchangeably would you prefer in different situations. So if the classes are separable or nearly so, SVM is better than logistic regression. Why not just use logistic regression? If we have the 2-class problem, you can do better than logistic regression with SVM, as long as they're reasonably separable. If they're all overlapping, SVM won't do very well. When they're not separable, logistic regression actually does better, and they recommend a penalized version, Ridge or Lasso. Logistic regression is nice because, as we were saying a second ago, it gives you these estimated probabilities. For each individual you want to make a prediction for, you get this really nice interpretable probability. My estimated probability this player is in the Hall of Fame is such and such. SVM just gives you numbers that are hard to interpret, if not impossible. And kernel SVMs are very popular in complex situations where linear boundaries and hence logistic regression and LDA don't work well. Okay, I will quit there. I hope you enjoyed the class. I hope you felt like you learned a lot. Thank you for your work. Thank you for being patient with me. I was overwhelmed a lot this semester. So I wish you the best in your studies. Keep in touch, and good luck. Okay? Have a good Christmas.